Now we've already talked about the first quantum number, also known as the principal quantum number, which represents the energy level of the electron involved. Now we're going to move to the second quantum number. And the second quantum number is the atomic orbital number. It's the general region in which the electron is most likely to reside. And this is an attempt to show how this works. This is also defined by what's known as the angular quantum number, or L. The first one was N. The angular quantum number, L, is an integer that defines the shape of the orbital, and it is any number from 0 up into n minus 1. So if the n for the electron is 1, that is, it's at the first energy level, then the only value for L possible is 0. If, on the other hand, the n equals 2, then the possible values for L are 0 or 1, and so forth. And so if you have L equals 0, you're in this area right here, which is a very small area, and it also represents a cloud approximately in this region where the electron might be found. The second one, L equals 2, is here, or excuse me, L equals 0 is right here, but n equals 2. So n equals 2 and L equals 0, so you have an area that looks something like this, which in 3 dimensions looks something like this. And then if n equals 3 and L equals 0, it looks like this, or like this. And these represents regions where the electron that has those two quantum numbers may be found. These define what are known as subshells. You'll notice that in each of these there's the little s here, 1s, 2s, 3s. This tells you that the principal quantum number is 1 and the angular quantum number, L, is equal to 0. This tells you the principal quantum number is 2 and the angular quantum number is 0. Principal quantum number is 3, the angular quantum number is 0. So S is defined by an angular quantum number of 0, P is defined by an angular quantum number of 1, D is defined by an angular quantum number of 2, and F is defined by an angular quantum number of 3. 0, 1, 2, or 3. So if an electron is n equals 1, L equals 0, then it's a 1s electron. If it's n equals 2, L equals 1, then it's a 2p electron, and so forth. Now the third quantum number is called the magnetic quantum number, and it represents, or it specifies, the z component of a particular orbital. Now by z component we're talking about the shape, which is shown here. Now, whether it's spherical or dumbbell or various other shapes that become more difficult to describe, these are the shapes. These represent the volumes that an electron can have. So M, you see here, you have P equals, you can have, M can equal anything from minus L to plus L through 0. So what that means is that in our first example, n equals 1, L equals 0, then M's only choice is also 0. And that's where we are right here. But now here, n equals 2, L equals 1, so you can have minus 1, 0, or plus 1. And so minus 1 would be px, 0 would be pz, and plus 1 would be py. Remember, p is determined by the second quantum number, L, and so each of these is 1, but if it's minus 1, it looks like this. If it's 0, it looks like this. And if it's +1, it looks like this. Now it gets a little more complicated when you get to the third. This is n equals 3, L equals 2. That means that m can equal -2, -1, 0, +1, +2. And here's what all those various things look like. And you can tell that it gets quite complicated as you go along. But that's the third quantum number. The shapes of s, p, d, and f orbitals, they can be constructed and described by the value of the magnetic quantum number or with the axis that defines their orientation. So if the magnetic quantum number is 0, that defines it. Or you can say pz, that also defines it. Or p1 defines this one, or py defines it, etc. This chart shows the energy that is related to the various electrons depending on where they are, their various numbers that they have. So for example, remember we had groupings. The principal quantum number starts with the groupings. And so you have a principal quantum number of 1, and L is 0, so the energy level is down here. The next quant is 2, the principal quantum number, but there is a little difference in energy between L equals 0 and L equals 1. Each one of these lines can hold 2 electrons, and we'll show you that in just a second. Then you get to n equals 3, and you have 3 very possible energy levels. L equals 0, L equals 1, L equals 2. And then 4, and interestingly, the 4, L equals 0, has slightly less energy than the 3, L equals 2. And we'll look at that some more in another slide. So the last quantum number is the spin. And the spin is either plus or minus 1/2. And it explains very small differences in electrons that are paired. And the spin determines whether it's a north-south pointing up, the magnetic field is north-south pointing up, or north-south pointing down. So electron spin determines its external magnetic field. So there are a total of 4 quantum numbers. N, the principal quantum number, shows the energy. L, the second quantum number, shows the suborbit or the angular quantum number. M is magnetic, and it shows the orientation within the subshell. And then S is the spin. And so here is a diagram showing the various capacities that occur. And remember, electrons fill in from the lowest energy to the highest energy. So you start at 1s, you move up to 2s, then you move to 2p, then to 3s, then to 3p, then to 4s, then to 3d, and so forth. And we'll show you this another way, and in the other way I'm going to show you is called the Aufbau principle. But there's something called the Pauli exclusion principle. The Pauli exclusion principle says that no 2 electrons can have exactly the same set of 4 quantum numbers. One way to think about quantum numbers is to think about them like an address on a street. Only one house can have any particular address on the street, and the house represents an area where a person lives. In this case, only one person can live in that house. And so if you have a set of 4 numbers that define one electron, that electron lives there and no other electron can be in that place. And that is the Pauli exclusion principle. This is a generalized energy level diagram for atomic orbitals, and it shows that when you can put a pair on each of these lines, but the pair will have opposite spins. So that's how they keep from having the same quantum numbers. The spin is the one that differentiates a pair from each other. So let's take a look first at hydrogen. Hydrogen is the simplest of all atoms. It has a single electron. If we were going to write the quantum number for this, and let me make this smaller so we can do that, we would write it this way. First of all, N would equal 1. L would equal 0. M would have to also equal 0. And S could be either plus or minus 1/2, but it would be one or the other. So if you had a line that represented the 1s level, you'd have one electron that was sitting in that level. So you can also write this as shorthand. This is the shorthand right here. This 1 is the principal quantum number. The S designation tells you the second quantum number is 0, because 0 is the same as S. The superscript tells you how many electrons are in this suborbital. But remember, these two numbers have to be different for the two, if you had 2 electrons here. And we'll talk about that in just a second, but let's take helium, which is the next element on the periodic table. It has 2 electrons. One electron's quantum number is exactly the same as hydrogen, just what we just showed. But the other quantum number for the other electron differs only in one way. And that is that S is negative 1/2 instead of positive 1/2. And so its symbol would look like it would be 1s2, and if you were going to represent it, it would be represented like this. So it would be 1 for n equals 1, s for 0, and then there would be 2 electrons, and that would be the electron configuration of helium. This is the electron, 1s1 is the electron configuration for hydrogen. Remember, I said that we were going to show the Aufbau principle, and this is the Aufbau principle, which is very similar to just what we talked about a minute ago. And the Aufbau principle says that you build the electron configuration in the order of the atomic number. And what that means is that you start with your atomic number of 1 up here, and you go to here. So this is atomic number 1, atomic number 2, then you bend up this way, atomic number 3, atomic number 4, and then here you can do 6, so 5, 6, 7, 8, 9, 10, 11. Wait, did I do too many? 5, 6, 7, 8, 9, 10. And then 11, 12. Atomic number 13, 14, 15, 16, 17, 18, 19, 20, etc. And that's how you build the configuration. Now you'll see, if you think about it for a second, that this fits very well into this periodic table. This periodic table, you start out 1s1, 1s2, and then now you're here at period 2, so all of these will start, you will have 1s1, 1s2, but then 2s, 1 and 2. Then when you're over here, you're at the L equals 1, so the P level, and then 3s, 3p. Then when you get here, that's when L equals 2 and you've got D levels. Down here, these are the F's. We won't get here very often. So the periodic table shows the electron configuration by subshell, and you can build up from the hydrogen atom This table can be used to determine the electron configuration of any element on this table. So we're going to stop at this point. You'll need to move on to the third section, and we'll finish up the lecture on the third section.